In Calculus 1, we use a general substitution rule to help us take an integral that might be difficult to compute and replace the x coordinate with a different coordinate system that might give us an easier to compute integral. Usually we saw a composition of functions and make the inside equal to the complicated function in the hopes that we will get an easier function to integrate. The problem is that if you're using a substitution, you also have to transform the differential. When you do this with the u substitution, that just basically means find the differential based on the equation by taking the derivatives of both sides. And just remember, the side that has the function is going to be replaced with a du, and the side that you took derivative with respect to x with is replaced with dx. You can then isolate for your variables and substitute things in, or just group your stuff together and get the appropriate transformation. Our goal is to be able to do this inside higher dimensions. That is, in two variable case, when we transform from the xy coordinate plane to a uv coordinate plane, or a three-dimensional case. So you transfer from xyz coordinate space into a different coordinate space, maybe something like uvw. To be clear, you have already seen very special coordinate transformations in the previous sections. When we introduced polar coordinates or double integrals of polar coordinates, we first gave you rules to change from rectangular coordinates to polar coordinates. Then we tried to understand what does that mean for differential areas inside of the polar coordinate system. But really, we just did a transformation or sort of substitution from one coordinate system to another, resulting in a way of transforming a surface or a region in rectangular coordinates into polar coordinates, or a polar coordinate integral. And in 3 dimensions, we had two choices: cylindrical coordinates, which is like polar coordinates in the base, and then you have a z direction over here. We would give you the equations that transform from rectangular to cylindrical, and we would figure out what the proper conversion should be for the differential, which ultimately gave us the cylindrical coordinate integral over here. And as we were able to see in this section, it wasn't the only possible choice of a coordinate system change. Instead, we could take the rectangular coordinates into spherical coordinates. So the same mathematical object computing the same kind of volume, but you do sort of equation description or function description of how do you go from, say, rectangular coordinates into spherical coordinates instead. And that has a consequence or a change on the integral formula for volume. Notice the differential actually has functions of your coordinate system inside of it. In order to do this in general for, say, 3-dimensional or 2-dimensional space, we have to give a systematic way of what do we mean by coordinate transformations, when should it work, and how do we actually get a new integral out of it, or a transformed integral out of it. So we will start these series of videos by describing what we mean by planar transformation. You can imagine a space transformation works in the same way, so it's good to start with planar, and then you can say that the characteristics we're looking for generalize to 3-dimensional space. So in the next video, we'll define what a planar transformation is with examples, what one-to-one actually means, and with examples how to tell when you have one-to-one. After we are comfortable with a planar transformation defined by equations between variables of, say, u, v, and x, y, we have to find the corresponding differential. So our trick to finding the corresponding differential is using the Jacobian. So we have to define what that is and show you how to calculate it. And once we've shown you how to find the Jacobian and how to calculate it, you can use it as a change of variables for double integrals in the planar case. So we'll show you how to apply both to get the change of variables double integral formula. And finally, all of these concepts generalize to 3-dimensional space. So if you just add in an extra variable, your complexity increases, but the rules and properties that you use to calculate the change of variables for a triple integral are exactly the same.